In section 4.5, we're going to look at a new technique for integrating functions that we haven't been able to do in the past, specifically when we've had something that doesn't fit what I've referred to as integral friendly, where it's a number, an x, and a power. Integration by substitution is something that'll help us integrate functions where there's more than just a plain x. Okay, before we start talking about this new technique called integration by substitution, let's take this derivative right here. Y equals 5x cubed plus 2x all to the fourth power. And since we don't see a plain x to a power, hopefully we're all remembering that that's going to be an application of the chain rule. It's stuff to a power, so when we take the derivative, we're going to bring the power down to 4. We're going to leave the stuff alone, the u alone on the inside, reduce the power by 1, and then we need to multiply by the derivative of that stuff, the inner function, which was 5x cubed plus 2x. Of course, that's nice and simple. You probably could have handled doing this in one step, but I just wanted to break it down into those two steps. Okay, so kind of changing gears a little bit, now let's talk about integrating. Let's suppose I wanted you to integrate this function. With what we know right now, how would we integrate this function? Well, it's not integral friendly right now. It's not a number, an x, and a power, so I guess we're kind of stuck here. But I'm kind of cheating in a sense on this first one, because hopefully you realize that this expression, this function here, is actually our derivative from above. Those two are the same. I just moved the 5x squared plus 2 to the front. So if this is really the derivative that we're trying to integrate, then of course the answer to this integral would be the original function. The antiderivative, or the original function, would be 5x cubed plus 2x all to the fourth power, and then don't forget that plus c. So how would we be able to do this problem if we didn't kind of cheat in a sense and take a derivative to figure out what this integral was? Well, maybe where we started in this problem by realizing it was a chain rule is a good thing to kind of get us going on this idea. Because simply put, we need to be thinking about this integral using this weird little saying right here. Euler-Nayak, if that's even how you'd pronounce that. And maybe you're catching on to what that really is getting at, but if you read it this way, you should be thinking about using the chain rule in reverse, because some problems are just chain rule problems in reverse. The thing that got us to this answer right here was using the chain rule. So if we wanted to go backwards and find the original equation, the antiderivative, we would have to think about the chain rule in reverse. When you run into problems like this, we're thinking about this technique called integration by substitution. And the little hint or clue that's going to give away that this is one of those types of problems is, do you see the derivative of a function and that same function on the inside of the integral? You'll notice 15x squared plus 2 was the derivative of 5x cubed plus 2x. And that's how we knew that this was a chain rule problem in reverse. So integration by substitution is just a technique for finding an antiderivative of a composite function when you have stuff to a power. This integration, the integration equivalent of the chain rule, is what we call a U-substitution. This integration by substitution is called a U-substitution. And that makes sense because we used the letter U back in our derivative days. So just to make sure we're okay with notation, because it's going to matter a lot in this section, when we wrote the notation d dx back in chapters 2 and 3, we were asking ourselves to differentiate a function with respect to x. Here in this chapter, when we see an integral symbol with a dx, we're integrating with respect to x. Okay, let's do this first problem that's going to require integration by substitution. And you'll notice right away we can't do this problem without some new technique, especially the one that we're learning in this lesson. So one quick note to make, mentioned this back in 4.1, but it's definitely worth mentioning again. When you're multiplying two functions, unfortunately, we can't take the integral of those separately. There is no product rule for integrating when you're multiplying two functions. So don't fall for that little mistake. If we're adding or subtracting two functions, then we can integrate those separately. But if we're multiplying, unfortunately, there is no quick way to do it. So one of the clues again that we're looking for is, do we see a function and its derivative in the integrand? Do we see it in our problem that we're trying to integrate? And in this case, we do. If I pull that 42 out to the front, it's just a constant. And if I realize that x squared plus 4 could be the function that we take a derivative of to get x, which is in front of the parentheses, then you'll be on the path of seeing that this is an application of the process called integration by substitution. So those U boxes that we were writing way back in 2.4 when we first learned the chain rule, we're definitely going to have to write in this lesson. With all of these problems, I'm going to ask that you guys write out this U box, because there's a little bit more going on in this U box than we've had before. So we're going to let U, because that's our stuff to a power, we're going to let our U be x squared plus 4. So instead of having x squared plus 4 in our problem, we're going to replace that with a U. So we have a dilemma. The dilemma is right now we're taking the derivative with respect to x, and we have x's and u's here, which is no good. We can only have that one letter that we're trying to integrate with respect to, and right now that's an x. So what we're going to have to do is we're going to have to come over to our U box and take the derivative of U just like we did back in chapter 2. Normally in chapter 2, we would have wrote U prime equals 2x. But we're not taking derivatives here. We're integrating in our problem. So instead of writing U prime, we're going to write a different version of U prime, and that would be du dx. Same thing as U prime, but we're going to leave that as the Leibniz notation, du over dx. And the reason we're going to do that is this. If we multiply that dx to the other side and make it the differential form, you'll notice I have an x and a dx right here. I have an x and a dx right here. And right now the goal is to get rid of those x's. We want this problem to just have u's in it. So what we can do is take that 2 and divide it to the other side. And then you'll notice we have an x and a dx, and all of that can be swapped out or substituted to become 1/2 du. And again, make note that this only worked because we had an x in this problem. If we didn't have this x right here in the problem, this wouldn't have worked. So I'm going to replace the x dx. I'm going to replace this x dx right here in the problem with a 1/2 du. And then everything feels a little bit better now. We have only u's in our problem, and we're integrating with respect to u. The one thing I'm going to do before we actually try to integrate this problem is take this 1/2 to the front. It really doesn't serve a good purpose leaving it there. So if we pull that 1/2 to the front, 1/2 times 42 is 21. And now this problem is very easy to do. We have a plain letter to a power. It doesn't even matter that it's an x or not. We have a letter to a power, and we're integrating that with respect to that same letter. So we have u to the 20th. All we need to do is add 1 to the power and divide by that number. And then don't forget that plus c. The 21s, of course, would cancel out. And the integral that we find, or the antiderivative, is u to the 21st power plus c. If we take the u that we originally called up here, x squared plus 4, and plug it in, we get a final answer of x squared plus 4 to the 21st power plus c. So hopefully you kind of noticed, if you reflect back on these steps, the name of the game is getting all the x's out of your problem and just making them u's. And the key to doing all of that stuff is using this u-box to do all that substitution. Make a note, usually you don't want to leave your answer with just the u's. You want to go back to the original variables in the problem. So of course plug that u back in, and that'll become your final answer. Just as a reminder, if you want to check your work, that's always available to you. If you take this derivative, which is your original function, you should get back to the original problem of where you started. And sure enough, when you take the derivative of this problem, you'll get back to the original problem that we started off with. Okay, now it's just time to practice a bunch of problems that require integration by substitution. Hopefully with each of these, you'll kind of see the technique of identifying when we're supposed to use it, and then the process of going through integration by substitution. So the first thing you should realize when you're doing problems is, do you see a function and its derivative in the problem? And it might not be identical. In that last example, it wasn't identical. But do you see it pretty close, if not identical? Well, in this case, we do. We see 5 plus x cubed as a function, and if we take the derivative of that function, we would see 3x squared. The other way you can look at this is we have stuff to a power. Remember this square root. If I rewrite this as 3x squared times 5 plus x cubed, that would be a 1/2 power. We have stuff to a power. So maybe that could be another way to look at it if you're not quite happy with the first way I explained it. If you see the stuff to a power kind of idea, like back in chapter 2, that stuff would have to be your u if it's not a plain x. Okay, so let's go ahead and swap out that stuff of 5 plus x cubed, and we're calling that u. And right here we have a dilemma. We have x's and we have u's in the problem, and we can't have that. So we're going to have to come over to our u box and take a derivative. So again, remember, we're not going to write u prime. We're going to write it as du dx equals 3x squared. And since we're trying to get rid of all the x's in our problem, if I multiply the dx to the other side with the 3x squared and make this a differential form, we can substitute. I see a 3x squared dx, I see a 3x squared dx here. All of that can go away and just become du. So we're just left with the square root of u du. And if we change that square root to a power, we can integrate that. We have a plain letter to a power, and we're integrating with respect to that letter. In other words, there are only u's in our problem. To integrate this, we'll just add 1 to the power and divide by that power. And if you flip that fraction from the bottom and make it 2/3, you'll end up with 2/3 u to the 3/2 plus c. And the last step is always going to be to take the u and plug it back in. So 2/3, 5 plus x cubed, all to the 3/2 power plus c. What are we going to do in this next one? Well, again, there's one easy way to identify this as an integration by substitution. Do you see some stuff to a power? Or if you want to look at it a different way, do you see a function and its derivative inside the integral? If you do, that's how you know this is an application of integration by substitution. So we can't have stuff to a power, so we're going to call that u. The x squared plus 1 will be our u. We have a dilemma here. We have u's with x's, so we have to come back to our u box and take the derivative. And unlike the first two problems, this is where I'm going to stop writing du over dx. You'll notice in the first two problems, I always sent the dx to the right side. So to kind of always skip over that step, just because these problems have enough steps as it is, You can always write du over dx if you want and then multiply the dx to the other side. But I'm going to just start writing the dx on the right side when we take the derivative. So we know 2x dx can all be switched out for a du. And you'll notice we have a 2x dx right here. All of that goes away and becomes du. And of course we have a 1 left in the top of that fraction. Now we can attempt to integrate this. 1 over u cubed we can write integral friendly by moving the power to the top and making it negative. U to the negative 3 power is integral friendly, and we're integrating with respect to u. We'll add 1 to the power, which is negative 2, and divide by that power, which is negative 2 plus c. If I move that negative power down to the bottom with the negative 2, we'll be left with 1 over negative 2u squared plus c. And like in the first two examples, we don't want to leave that u in the final answer, so we'll put the u back in, and the u in this case was x squared plus 1. In the last example, we have a trig example, and again, be very careful. There is no such thing as a product rule when we're integrating. So unfortunately, we can't take the integral of sine separate from cosine. So how are we going to do this problem? Well, again, do we see a function and its derivative inside the integral? If you do, that's how you know that could be an application of integration by substitution. And you'll notice I'm highlighting sine x right here because if I call that u, the derivative of sine x is cosine x. And that's great because that's how we identify that the chain rule is what originally got us to this derivative of sine x times cosine x. So let's go ahead and substitute. We're calling sine x u, so now we're going to replace that with a u. Again, we have the dilemma just like the previous problems. We have u's with x's here, and we can't have that. So we've got to come over to the u box and take a derivative. The derivative of u is du, the derivative of sine x is cosine x dx. Wherever I see a cosine x dx, we're going to swap it out for a du. And of course, we see a cosine x dx right here. So all of that becomes du, and we've achieved what we were trying to do. We have all u's over here, and it is integral friendly because we have a power of 1 right here. So we can go ahead and apply the power rule. We'll add 1 to the power, which is 2, divide by that power, which is 2, and add a c. Again, you don't want to leave that u as the final answer. You're going to take that u and plug it back in. So it's going to be sine squared over 2 plus c. Okay, moving on with some more examples of integration by substitution. What about problems that aren't obvious? Unlike the ones you just saw where we had stuff to a power, and maybe that's the way you determined what the u is going to be. How is this problem an application of integration by substitution? Well, again, just like you saw back in Chapter 2, we can only take a derivative in Chapter 2 if it was a plane x. Same thing goes for Chapter 4. We can only integrate if we see a plane x. If you don't see a plane x, that has to be your u, because it's a composite function, and we're trying to integrate that composite function. So we're going to go ahead and call 4x u. Again, like the previous examples, we have a dilemma. We have u's with x's, and that's no good. So we have to come over to this u box and take the derivative. The derivative of u is du, the derivative of 4x is 4 dx. But you'll notice something. I see a dx in my problem right here, but I don't have a 4 there. And that's okay. We can just send that 4 over with the du, which would make it 1/4. When we divide it to the other side, it'll become 1/4 du equals dx. And since we know now dx is equal to 1/4 du, we can replace that dx with a 1/4 du. I believe this will be the last example I do this way, because anytime you end up with these constants, you should always pull them to the front. So if you want to just save yourself a step in future problems, just always write that constant out in the front. So that's what we're left with. 1/4 times the integral of cosine u du and that's great. We have only u's in our problem, so now we can integrate cosine u. The integral of cosine u, we know. That is just sine u plus c. Again, we don't want to leave the u in our final answer, so we're going to plug u back in, which happened to be 4x. So the answer is 1/4 sine 4x plus c. I don't want to totally focus on only doing indefinite integrals, so let's make sure we're still okay with the concept that we learned in 4.3 and 4.4. When you want to find the area of a region, we need to set up an integral. And in this case, we want to find the area between the curve and the x-axis that you see shaded here in yellow from -1 to 1. So the first thing we have to do is set up that integral. The reason this problem exists here in this lesson is because this is going to require integration by substitution. I see that we have stuff to a power, so that stuff needs to go away and just be a plain letter, and in this case we're going to use the letter u. So if I replace the x cubed plus 1 with u, we have a dilemma again. We have x's with u's, which is no good, so we have to come over to our u box and take a derivative. The derivative of u is du, the derivative of x cubed plus 1 is 3x squared plus, dx. You'll notice we have an x squared dx in our problem over here, but we don't see a 3. Just like the previous example, that constant we can move to the other side. And now that we have an x squared dx by itself, I see an x squared dx right here. All of that goes away and just becomes 1/3 du. And you'll notice in this example, I went straight away to moving that constant out to the front of the integral. Okay, once you kind of get all that stuff out of the way, you should have something you can integrate. And in this case, u squared is easy to integrate. We'll add 1 to the power, which is 3, divide by that new power, which is of course 3. In this problem though, be careful, there is no plus c because this is a definite integral. We're trying to find the area here. So we're going to put the bar, and then the lower bound of -1, and the upper bound of +1. If you clean this up a little bit, 1/3 and the 3's in the bottom there become a 9, so 1/9 u cubed. And then of course we need to plug the u back in. X cubed plus 1. Once you simplify and plug the u back in, now you can take what you learned in 4.4 and apply it here. And you'll notice something, and I think it's important. Anytime you have a constant in front of your function, I would leave that constant out in the front and then apply the fundamental theorem of calculus. Take the top bound, plug it in, which is +1. Take the lower bound, plug it in, which was -1, and then you subtract those two values. So if you do the math here, you're going to find that when you plug in the 1, 1 plus 1 is 2, 2 cubed is 8. You're going to get -1 plus 1, which is 0. And then when you do 1/9 times 8, you'll get 8 over 9. And that is the area from -1 to 1 between the curve and the x-axis. So if you think back to that last example I just did, we had to plug our u back in so that we could take the upper bound and the lower bound and plug them in so we could find our final answer. In problems that require something called a change of variable, you actually don't need to do that. So let's take a look at what I mean in this example. So first thing we got to realize here, is this a application of integration by substitution? Is this a U-substitution? Well, the short answer is yes. I see stuff to a power. I see a function x squared plus 1, and I see its derivative, or part of its derivative, which is the x in the front. So this is definitely going to be an application of our U-substitution. So if we kind of go through the whole U-box thing, take the derivative, and since there is no 2 over here in our problem, move over the 2 by making it a half. We can go ahead and do this all in one step now. The x squared plus 1 becomes u. The x dx, which you see right here, becomes 1/2 du. And again, that 1/2 I'm going to put in the front of the integral. And now we're good. We have only u's in our problem, so now we can apply the power rule. It's a plain letter to a power, so we're going to add 1 to the power and divide by that number. But before I do that, I'm going to stress something here. That 0 as the lower bound and that 2 as the upper bound are x values. So I'm going to just stress that. I hope I'm not confusing too much here. I'm going to just stress that by writing x equals 0 and x equals 2, and you'll see why in a moment. So when we add 1 to the power, we get 3, and when we divide by 3 and multiply it by that half, we'll get 1/6. And when we put the bar, again, I'm going to emphasize that the 0 and the 2 are x values. So we can't plug them in right now. It's u cubed, and those values are x's. So we can't just plug in the top bound and the lower bound right now. If you plug the u back in, which has x's, now we're able to plug in our upper and lower bound by the fundamental theorem of calculus. So let's go ahead and do that. And again, this constant here in the front, I would just leave in the front, kind of ignore it for a second, and go ahead and apply the fundamental theorem of calculus, where you take the top bound and plug it in, so 2 squared plus 1, and then you take the bottom bound and plug it in, which would be 0 squared plus 1 cubed. And then we're going to subtract those two values. When you plug in the 2, you'll get 125. When you plug in the 0, you'll get 1. 125 minus 1 is 124, times 1/6 will give you a reduced fraction of 62/3. So I said something before about maybe a different path we could take on this problem. And that path is right here. You heard me say you can't plug the 2 in and the 0 in at this step. But what we could do actually is change those bounds that are x's over to u's. And that would be perfectly legal. We know that u is x squared plus 1 over here from our u box. Since we know u is x squared plus 1, that would mean the upper bound of 2 would be 2 squared plus 1, and that would be a u value. The lower bound would be 0 squared plus 1, and that would again now be a u value. So those two new bounds are 5 and 1. And since these are both u's, I never put it here, but that's a u right there, and that's a u value right there, now we can go ahead and plug in using the fundamental theorem of calculus. If you plug the upper bound in of 5, you'll get 5 cubed, which is 125. If you plug in the lower bound and cube it, that would be 1 cubed, which is 1. So we still get to the same result. A little bit different path, but we still get to the same result. My recommendation would be really never to change your bounds over to u values. It just kind of produces more possibilities, so to speak, for making extra errors. So I wouldn't anticipate many of you all trying to do the problems that way. So I guess the question is, then why are we even talking about this? Well, on the AP test, there are going to be problems that will test you on this idea of also needing to change the bounds when appropriate. So in this problem right here, which is multiple choice, they're telling us what the substitution is. They're telling us u is going to be 2x plus 1. So if we change our problem to be that, it's just going to be the square root of u dx. But to emphasize, that x of 0 and that x is 2 for our upper and our lower bound. So here's the thing. We don't have to change our bounds over to u's. You'll notice in the problem above, the first way I did it, I never had to change my bounds. But the key here is they want us to find an equivalent expression. Because we want to find an expression that's equal to the original one, as soon as you start changing things to u's, everything has to be u's, even the bounds. So if we do our little u box here, you'll notice that u is 2x plus 1, du is equal to 2 dx, and there is no 2 in our problem over here. So we would have to take that 2 and divide it over, which would make it a 1/2. Wherever we see a dx, we'll replace it with a 1/2 du. And again, that 1/2 we can put in the front. But like I was saying a minute ago, we're looking for an equivalent expression, so all the values have to be u values. We have a square root of u du, which is great, but we also have to change those bounds of x's over to u's. And you'll notice the bound of 0, when you use your u over here, just like in the example we did before, if x is equal to 0, that would mean u is equal to 1. If x is equal to 2, 2 times 2 is 4 plus 1, which is 5, and that gives us that final answer there. So again, to recap, you don't really ever want to do a change of variables unless you have to. I think for most of us, we're happy just leaving them all as x's and going through those steps, but just note, in certain problems you might be forced to change your bounds over to u's, and then proceed through the problem with those values.